Alright, so this is 4445 CPCTC and isosceles triangles, equilateral triangles as well. Okay, so up to this point we have proven triangles congruent in many different ways, either definition of congruent figures, side, 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 angle, 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 side, hypotenuse, leg. And once we've proven triangles congruent, we can say that any part of the triangle is congruent to each other. For example, let's say I have two triangles. And let's say that with these two triangles, I have enough information to prove them congruent. So let's say they're congruent because of side, angle, side. Right. Triangle ABC is congruent to triangle DEF because of side, angle, side. Once I've proven them congruent, I can say that any corresponding side of them are congruent. So let's take a look at B and E. I already know that these two triangles are congruent. These two guys, angle B and E, they're twins, they're matching, they're corresponding. So after I prove them congruent, I can say that any corresponding side or any corresponding angle is congruent. So I can say that angle B is congruent to angle C because a something called corresponding parts of congruent triangles are congruent. I call it for short CPCTC. Corresponding parts of congruent triangles are congruent. Corresponding parts of congruent triangles are congruent. And it's used a lot with triangles and with quadrilaterals and other shapes to prove things congruent. I can also say side BC is congruent to side EF. Why? Since I already know that they're congruent, any corresponding or matching or twin these guys can be congruent. CPCTC. Corresponding parts of congruent triangles are congruent. So with that in mind, they give me this figure here. The AED, ACB. Here we have these guys congruent, these guys congruent. I can use vertical angles to say that these two guys are congruent. So, doing the proof, they want to prove that angle C is congruent to angle E. So, this is probably what a 4-step proof. BA is congruent to DA. CA is congruent to EA. That's given to me. I can also say that angle CAB is congruent to angle EAD because of side, angle, side. So these two triangles are, vertical angles. Then I can say the two triangles are congruent. Triangle CAB is congruent to triangle EAD because of side angle side. Once I've proven the triangle is congruent, I can prove any corresponding side or any corresponding angle congruent. So then I can say C is congruent to E. And I can say that because of corresponding parts of congruent triangles are congruent. Okay, here. Okay, so for this triangle, we have B, M, C. I'm assuming that's A. We're told that these two guys are the same, and we're told that M is the midpoint. So since I know that M is the midpoint, then I can say that these two guys are congruent. And then after that, I can say that this guy is congruent to itself, so I can say that both of these two triangles are congruent because of side, side, side. And then after that, I can say any corresponding in there is the same. So this case would be AMB and AMC. So that's the thought process for this proof. So that's like a 4 or 5 step proof. So given AB is congruent to AM or AC, and M is the midpoint of BC. M is midpoint of BC. So since I know M is the midpoint, then I can say that BM is congruent to MC, definition of midpoint. Then I can say that AM is congruent to itself, reflexive property. Then I can say that the triangles are congruent. So triangle AMB is congruent to triangle AMC. And I can say they're congruent because of side, side, side. Okay. Once I have the triangles congruent, I can say that any corresponding part of them are congruent. Therefore, I can say that angle AMC, or AMB rather, is congruent to angle AMC. Corresponding parts of congruent triangles are congruent. 5 steps. Okay, so that's 4, 4. Now 4, 5. Isosceles and equilateral triangles. There are 1, 2, 3, 4, 5 theorems in this one. Alright, so we have an isosceles triangle. An isosceles triangle means that I have at least 2 congruent sides. At least. and I have certain things associated with it. The angles opposite of the congruent sides are called the base angles. Base angles. The angles that are not opposite of the congruent sides, these guys are called the vertex angle. And then the the congruent sides of the isosceles triangles, these guys are called the legs. Okay? Isosceles triangle, that are a pair of a triangle with a pair of congruent sides. The angles opposite of those congruent sides are called the base angles, and the angle that is not opposite of the congruent sides is called the vertex angle, and the congruent sides are called the legs. Isosceles triangle theorem, or sometimes known as base angles theorem. So isosceles triangle theorem. What the isosceles triangle theorem says is that if I have two triangles, or actually if I have a triangle, A, B, and C, and I know that two sides are opposite, not opposite, two sides are congruent, the legs are congruent, then I can say of that same triangle, A, B, and C, then I can say that the angles opposite them are congruent. So if AB is congruent to BC, then I can say that angle A is congruent to angle C. Isosceles triangle theorem. If two sides of a triangle are congruent, then the angles opposite of those sides are congruent. If two sides of a triangle are congruent, then those angles opposite of those two sides are congruent. Isosceles triangle theorem. And with an isosceles triangle theorem, there must come a converse. Oh, here's the proof. Let's see. Given xy bisects, or xb bisects xyz, okay, so here's the proof of the isosceles triangle theorem. And it says this: we have a triangle. We're given that the two sides are congruent, the legs are congruent. I guess this is triangle YXZ. We have a line XB such that XB bisects YZ. Alright, so that's our given. Alright, so number one, XY is congruent to XZ. This is proof of the isosceles triangle theorem. And then we can say that XB bisects. So essentially we're drawing an auxiliary line. Bisects YZ. Okay. Well, if that's the case, then I can say that YB is congruent to BZ. Definition of midpoint. Then I can say that XB is congruent to itself, reflexive. Then I can say that the two triangles are congruent because of side, side, side. So XYB, triangle XYB is congruent to triangle XZB because of side, side, side. And then lastly, any corresponding side within two congruent triangles are congruent, so that I can say that angle Y is congruent to angle Z. CPCTC. Proof of. Isosceles triangle theorem. And then we have the converse of the isosceles triangles theorem. So if we have a triangle ABC and we're given that we have the two angles congruent, the base angles are congruent, then we can say that the two sides are congruent, opposite of those angles. So this is the converse, or isosceles triangle theorem converse. And it says that if angle A is congruent to angle B, then AB is congruent to CB. Okay? That was set up a little differently, but oh well. If two angles of a triangle are congruent, then the sides opposite of those angles are congruent. Okay, so we can use these quite a bit in algebraic situations. It says WVS is congruent to S is TR congruent to TS. Alright, so WVS is congruent to angle S. Yes. So here's WVS right here. Here's angle S. Since the two sides are congruent, the isosceles triangle theorem says that the two base angles are congruent. So S is congruent. Now, what I'm going to do is I'm going to draw it like this. R, T, S. Okay. Then we have this other side right here, this guy. W. Alright, and this is V. And then we have this scenario here just to throw you off. That's too even. Here we go. U. We are told that these two guys are the same, right? Or we're told that this is this. Because of isosceles triangle theorem, if the two legs are congruent, then the base angles are congruent. So yes, this guy is congruent. So then we can say that angle WVS is congruent to angle S. Isosceles triangle theorem. Okay, but now look what we have. At the same time that WVS is congruent to S, we have this R, and R is congruent to V, so that means that R is also congruent to S. So then we have enough information to say that side TR is congruent to side TS. I can say that this side and this whole side are congruent because of isosceles triangle converse, which says that if the base angles are congruent, so isosceles triangle converse, if the base angles are congruent, then the sides opposite those base angles are also congruent. So I have enough to say that TR is congruent to TS. Right. So then we have something called theorem 4.5. And what theorem 4.5 says, which is essentially an angle bisector theorem, actually. But they won't call it that. They should though. And what this says is that if I have a triangle A, C, B, or ABC, and I draw a line that I know cuts this guy in half, so angle C is congruent to angle, or AC, we call this D, is congruent to BCD. If I draw a line that bisects the vertex angle, because I know that this is an isosceles triangle, this is the vertex angle, then it is also perpendicular. It is also the perpendicular bisector of the base. So this is the base, because I have the base angles. This is perpendicular. Actually, I'll do it in blue. This is perpendicular, this is perpendicular, and since it's a bisector, it's going to cut that in half as well. Right? So if AC is congruent to BC, meaning I have an isosceles triangle, and angle ACD is congruent to angle BCD, which makes this a angle bisector, then I can say that this is also a perpendicular bisector of the base. Then CD is perpendicular to AB, and AD is congruent to DB. Alright, it's perpendicular and it cuts it in half, which is neat. So we have a scenario here. I'm told ABC. So it's A, B, C, and then D. I'm told that these two guys are the same, and I'm told that these two guys are the same. So this sets up the situation for making this a perpendicular bisector. So I'm told that A is 27, so this guy is 27. What is the measure of X? And X would be right here. What is this guy? Since I know, this is what the book wants you to do. Since I know that this is the same as this, and this is an isosceles triangle, then I know that this is perpendicular, because this is the definition of theorem 5.4.5. It's perpendicular, and these two guys are congruent. So if I focus on this triangle here, triangle ABD, I know that this is a right triangle, so this is 90 degrees. I know that this is 27, and I'm looking for this guy. Since these two guys are the same, if that's X, then that's also X. So I know that the sum of triangles add up to 180 degrees, so 27 plus X equals, or plus 90 also, because there's a 90-degree angle, equals 180. So that's x plus 27 equals 90. So x equals 63. Right. Which makes sense. I would have done it another way. And this is the way I would have done it. For those who, there's so many different ways to solve this, but since I know that this is 27, then I know that this guy is also 27. Instead of calling this x, I would just call this 2x because I'm adding them together. So then I can say that 2x plus 27 times 2, which is 54, equals 180. This is what I would have done. Then it would have been 2x equals 130, 126, and then x equals 63. Again, you would have gotten to the same way, same thing, either way. I just decided to show you an alternate route. Okay, so method number 1, method number 2. All right, so 2 more. We have something called corollary, and the corollary is a it's an additiveness. Additive. It's a theorem that can be proved easily from another theorem. I call it like an additive. So it's a theorem. It's like an add-on theorem to our original theorem that can be proven easily. I don't know how easily is subjective from using another theorem. Corollary. So for corollary to theorem 4.3 and 4.4, so that's corollary to the Isosceles triangle theorem and the corollary to the Isosceles triangle converse, we can get something to do with equilateral triangles. So let's say we have an equilateral triangle, and remember, equilateral triangle is a triangle where all 3 sides are congruent. Now we've already said that for the isosceles triangle that the base angles are congruent, but if all 3 sides are congruent, then we can just add on that extra vertex angle up here. Since they're all the same, the side opposite of them must all be the same in terms of the angles. So then I can say that, and that's what they mean by easily adding on. We're adding on a 3rd congruent side to this triangle as opposed to 2 like the isosceles triangle theorem. So if we can say opposite of these 2 guys are congruent, then why can't we say opposite of 3 guys are congruent? It would make a lot of sense, right? And that's what they mean by easily adding on. So this is a corollary to isosceles triangle theorem. And that says that if AB is congruent to BC and is congruent to AC, well, then all the opposite angles are congruent. Angle A is congruent to angle B is congruent to angle C. Corollary to isosceles triangle theorem. If a triangle is equilateral, then the triangle is equiangular. Voila. Likewise, we can have the corollary to corollary to the isosceles triangle converse. So doing this in reverse. So now instead of having congruent sides, we have an equiangular triangle, meaning all the angles are congruent. So just like before, for the isosceles triangle converse, we said if the base angles are congruent, then the sides opposite of those base angles are congruent. Well, if we were to add on to this theorem, easily of course, if we added a third angle, well then maybe that also means the third side, right? So all three sides are congruent. So that is what a corollary is. We added additional piece that's already used in a original theorem. Corollary to isosceles triangle converse. Alright. So if angle A is congruent to angle B is congruent to angle C, then AB is congruent to angle BC is congruent to angle AC. If a triangle is equiangular, then the triangle is equilateral. Okay. And with that, you can do various mathematical things. So if we look down here, let's see. A, B, C. Things to note. If if a triangle is equiangular, or equilateral, right? Meaning all the angles are the same. So we can call this angle X, angle X, angle X. We know that the sum of angles inside of a triangle equals to 180. Combine like terms, divide by 3, X is equal to 60. This is always the case. In equilateral triangles, or the angle will always equal 60 degrees, all three of them. Because 60 plus 60 plus 60 equals 180 degrees. There is no other angle that it can equal if they are equilateral triangles. Okay? Always, always, always. So if we know that they're equilateral, we'll always be able to find angles because they will always be 60 degrees. Okay? Alright, well, this section is going to really utilize less theorems in it, so more solving for X. It's more algebraic in nature. So, a couple examples here. They gave me this triangle. I know these two guys are the same, and they give me the base angle of 70. So, they want to know the measure of angle A. So, if this is 70, I know that these two guys are the same, so this guy is also 70. Why? Isosceles triangle theorem. Same thing here. If this is 53, then I know that this is also 53 because the guys are congruent. Here they want the value of X. If this is 30, that's the vertex angle. These two guys are the same. So if this is 30, I know that these two guys are the same. right? So if this is x, then this is also x. They're the same. So I can say x plus 30 equals 180. I can combine like terms, 2x, and subtract 30 from both sides. X equals 75. Yeah. Same thing for this guy here. Knowing certain scenarios. Oh no. Good enough. This guy and this guy. I know that these two guys are the same. So here I have a situation where, where's the 42? I'm assuming the 42 is over here. Because this is a scenario of a perpendicular bisector, meaning that this guy is 90 and this guy is 90. The theorem for the 4-5, saying that if I have an isosceles triangle and I have this guy cut the angle in half, then this is a perpendicular bisector. So ways to solve this. Remember I showed you two different ways. So this is 42, then that's 42. And then I can say that that's x. So I can say that it's 2x plus 42 plus 42 is 84 equals 180. So 2x equals 100 take away 4, 96. X equals 48 degrees. So that's the way that I usually do it. The way that the book wants you to do it, since I know that that's 90 degrees, I can say that 42 plus 90 plus x equals 180. So that's 132 plus x equals 180. So that's 50, 48 equals x. Either way, they'll get you to the promised land. Alright, so that's that section. Hope you have a great rest of your day.